Is this magic or science? Maybe both magic and science? No, it's just science. But how is this happening? Let's find out together in this episode all about magnetism. If you've ever put a reminder on the fridge, or used a compass to find your way in nature, or played with crazy toys like these, you've witnessed magnetism.
A magnet is any material or object that produces a magnetic field. The most common magnet that you'll probably see is a bar magnet like this. But magnets come in all different shapes and sizes, from this horseshoe magnet to the entire planet Earth, which is basically just one huge magnet. We'll come back to that. Whatever the size or shape of the magnet, they all have a few things in common. They all have two poles, a north and a south pole, and they are all surrounded by a magnetic field. Magnetism is a force that is exerted by magnets when they attract or repel certain materials. That pulling force is called attraction, and when a magnet exerts a pushing force, that's called repulsion.
If a material is pulled or attracted by a magnet, then the material is called magnetic. This squishy fish is not magnetic, but these paper clips are. This plant is not magnetic, but these nails are. You'll notice that most of the things that are attracted or stick to magnets are metal. Metals like iron, nickel, and cobalt are some of the most magnetic materials. But just because something is metal doesn't mean that it's magnetic. We can see this when we move a magnet over some aluminum. Nothing. To really understand magnetism, we need to observe what is happening down at the atomic level.
You may already know that all matter is made of atoms, the building blocks of everything. Atoms are then made up of even smaller particles like electrons that carry an electric charge. In most materials, these electrons are spinning around the outside of an atom in all different directions. In magnets, the electrons are all spinning in the same direction. This creates an electric current, which causes the force of magnetism.
Because all of the electrons are facing the same direction, there is a clear front and back to a magnet. We call these ends the North Pole and the South Pole. Most magnets are marked with an N for the North Pole and an S for the South Pole. These poles are what determines if your magnets will attract or repel. If you match a north pole of a magnet to a south pole of another magnet, then they will attract. However, if you try to place together two north poles or two south poles, the magnets will repel. This repulsion force is what allows this magnet to levitate or float. So like poles repel and opposite poles attract. It's important to know that magnets always have poles. So if you were to slice this magnet in half, you wouldn't just end up with one magnet that is a North Pole magnet and the other only a South Pole magnet. You would actually end up with two smaller magnets with both a North and South Pole.
Those aligned spinning electrons also create a magnetic field. Magnetic fields are invisible and surround a magnet, creating a magnetic force. That's how magnets can attract or repel things without even touching them. We obviously can't visibly see the magnetic field, and magnets aren't always labeled with a north or south pole. But we can use iron filings to visualize the magnetic field.
These iron filings are magnetic, so they will align with the magnetic field, making it visible. This is really impressive. The iron filings show us the pattern of the magnetic field, but they don't show us the direction, like which end is the north or south pole. This is where compasses can help.
If you're still here, liking this video, let us know. And hit that subscribe button so you never miss an episode.
We can easily find the poles and the field lines of the magnetic field by using a few compasses. The needle of a compass is actually a tiny little bar magnet and will always line up with the field lines of whichever magnetic field it's placed in. And it will always point toward the south pole of a magnet.
You may have just asked that if compasses always point toward the south end of a magnet, then why do they always direct us north? The short answer is that Earth's geographic North Pole is actually physically a magnetic south pole. More on that in a bit.
If we put our compasses near our magnet, we can draw an arrow in the same direction as the compass needle, and as it's heading toward this magnet end, we know that this must be the South Pole. Similarly, if we place the compass over here, then our compass needle would be pointing away from the magnet. So this must be the magnet's North Pole. By doing this over and over again in different places, we would eventually recreate the same pattern as our field line diagram from before. We show a magnetic field in 2 dimensions on paper, but the magnetic field extends out in 3 dimensions. This oil is ferrofluid, and it's going to help us see some of the magnetic field in 3 dimensions. The fluid is attracted to the magnet's poles and forms these flexible, soft spike shapes as it gets closer to the magnet. We can see that the north and south poles form these shapes. When we put the magnet on its side, the fluid changes and only makes spikes near the poles.
The strength of a magnetic force depends on 2 things: how powerful the magnet is, and 2, the distance from the magnet. We can increase the magnetic force by using a stronger magnet, or we can increase the magnetic force by stacking 2 low-power magnets with their north poles facing the same direction.
We can test the magnetic force of these 3 magnets using wooden blocks. Here, I have a magnet on wheels, which allows it to move freely. Let's first test this low-power magnet. The low-powered magnet was able to attract the magnet on wheels with only 1 block of separation. Now let's test the other 2 magnets. As you can see, the high-powered magnet could attract the magnet on wheels at just under 3 wooden blocks, making it the magnet with the greatest magnetic force.
Not all magnetic materials are truly magnets. An actual magnet is any object that produces a magnetic field, while a magnetic material is any object that is influenced by a magnetic field and has the potential to become a magnet. There are permanent magnets and induced magnets. Permanent magnets are always magnetic, meaning that their magnetism or magnetic field can't be turned off. In contrast, induced magnets aren't always magnetic. In fact, they're unmagnetized most of the time. When placed inside of a magnetic field, induced magnets act like a magnet, attracting magnetic materials.
Iron and steel can be induced magnets. If you place an iron paperclip close to a permanent magnet, even without touching, the paperclip becomes an induced magnet. The paperclip is inside the magnetic field. The end of the paperclip nearest the magnet now has the opposite polarity because the paperclip is now an induced magnet. We can see this when we add another paperclip and another. This is a temporary process. If we remove the original paperclip from the magnet or the magnetic field, it will lose its magnetism. No magnetic field, no magnetism.
One of the biggest permanent magnets out there is actually the Earth itself. The core of the Earth is made up of molten iron and nickel, so the movement of those liquid metals creates a magnetic field over the entire planet, complete with its own poles, just like any other magnet. The terms North Pole and South Pole can be really confusing. The geographic poles mark Earth's axis of rotation seen here, but the magnetic poles are different. The magnetic poles exist because of the way that the atoms are arranged in Earth's iron core. This area is the geographic North Pole, and this area is known as the magnetic North Pole, which is confusing. Think of it like the magnetic pole that is located in the north, not physically the north magnetic pole. It's physically a south magnetic pole, attracting the north-seeking end of a compass. I know. It hurts. More importantly, you should know that this immense magnetic field deflects high-energy charged particles that race towards us from the sun. Without the Earth's magnetic field, life here on this planet probably wouldn't be possible. So the next time you're enjoying nature on a sunny day, remember to thank that wonderful magnetic field that is shielding you like an enormous umbrella. And if you want to learn more science, you can check out this video next.